Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be briefly talking about organic molecules. So one of the reasons why I really wanted to do this is because organic molecules really are one of the most versatile set of molecules in nature. And they're very common in biological systems. And I love being able to talk about realistic molecules as we go through chemical reactions and various chemical molecules. So in order to do this, I want to briefly overview some of the major features of organic molecules so you can be kind of familiar with the nomenclature as I use it. So when we're talking about organic molecules, really what we're talking about is molecules that are principally composed of carbon and hydrogen. This is one of the reasons why they're so common in biology, because biology is using a lot of carbon and hydrogen, but we also see a fair bit of other atoms, such as oxygen, nitrogen, phosphorus, and sulfur. You put these all together and we get the classic acronym of SHNOPS, CHNOPS, because these are really what are really the molecules of life. And it includes all sorts of relevant chemical compounds, including things like arginine and lysine, which are amino acids. And these essentially are the building blocks of proteins, along with histidine and 17 others. We also have things like nucleic acids, which is the building block of DNA, fats, sugars, drug molecules like morphine. All of these things of life are organic compounds, and they are mainly a feature of several reoccurring motifs. So when we're talking about organic molecules, one of the most simple type of organic compounds I can deal with are called hydrocarbons. And they're called this because they are made just of hydrogen and carbon. You probably know hydrocarbons is another way people talk about, say, fossil fuels, because fossil fuels are also typically made of hydrogen and carbon, and that's kind of it. Now, there's a huge range of hydrocarbons, but one of the simplest kinds is called alkanes. And this is molecules where we only have single bonds in between carbon and hydrogen. So everything has the minimal necessary connection, and it's just carbon and hydrogen. And you can tell an alkane because they have a suffix of ane. It's really that easy. Now, in order to identify the alkane, we also have to watch out for the prefix of the molecule. So ane tells me I'm dealing with an alkane, but the prefix tells me how many carbons are present. 1, 2, 3, 4, 5, all the way to 10. Now, this can be a little bit tricky to keep straight of who's who. The acronym that honestly really helped me figure it out as a senior chem student is this very important piece of advice: meth eats people's brains. Methyl, ethyl, propyl, butyl. 1, 2, 3, 4. That gets you the first 4 molecules. So it tells you how many carbons are present. And then you just need to saturate the system with hydrogens. From there, we can go ahead and use geometry just like we did previously. Pentagon, hexagon, heptagon, octagon, nonagon, decagon. And we can use this to figure out the number of carbons from 5 up. So meth eats people's brains, and then just remember your geometry, and you should be able to figure out the number of carbon atoms present in a system. Now, one of the most simple modifications we can do to one of these alkanes is we can go ahead and replace 2 of these hydrogens with an extra double bond. So if I remove two hydrogens and add in a double bond, what we now have is called an alkene. And these will all use the ene suffix. And there's several of these that you may be familiar with, such as ethene. You may know this most frequently as polyethylene, which is a major plastic, where you pretty much take a whole bunch of these ethenes and chain them together to make a long chain of carbon. So that's how we get polyethylene, is we base it off of ethene, which has the older name of ethylene. So this also applies for any number of longer chain molecules. So for example, you can also have propene, where I have 3 carbons and a double bond, or butene, or pentene, or hexene. All of them will have essentially a as many carbons as the prefix has, and then this "ene" suffix letting me know that there's some kind of alkene. Now you can repeat the same process for a triple bond, where I remove 2 more hydrogens, put in an extra bond, and I get ethyne, more commonly known as acetylene. Again, an older common name. So this is what you use when you're doing welding. And again, all of these triple bonded molecules are called alkynes, and they'll all use the "ine" suffix, whether again you're looking at ethyne, propyne, butane, or so forth. So again, the real trick when trying to identify the type of hydrocarbon is looking at that suffix. "Ane" for a single bond, "ene" if you have a double bond, "ine" if you have a triple bond. And as you typically add these extra bonds, they're allowed to do a lot more reactivity. And so you get some really fun chemistry as you go to double and triple bonds. Now, while hydrocarbons essentially form a good base for organic molecules, you can essentially put a whole bunch of other different groups attach these carbons to essentially produce a wide array of chemistry. And as I put on these groups, we call these groups functional groups. And as I change the functional group, I tend to change the properties of the molecule. So one of the simplest functional groups, and one that you're probably well aware of, is alcohols. So the idea of an alcohol is I replace one of those hydrogens with an OH group. So I have an O attached to an H. And these all, just like alkenes and alkynes, also have a constant suffix. In this case, all. And you're probably familiar with a fair number of these molecules. So if I take methane, and add in an alcohol, I get methanol, which again, you should watch out for, because if you drink this, it sends you blind. And no, that is not a joke. It is actually how in Prohibition they cracked down on illegal alcohol, is they used wood alcohol to spike the system, and anybody who drinks methanol can go blind or even die if they drink it in large enough concentrations. And this was to dissuade people from drinking the 2-carbon derivation of ethane. So if I take ethanol, so if I take ethane, I replace a hydrogen with an alcohol, I get ethanol, the the classic fermented beverage. Now you can also do this for propane. Again, 3 carbons, replace one of the hydrogens with an alcohol, and you get propanol. You may know the form of propanol you may know the most is isopropanol, which is used to help clean wounds. And you can also use you can do this with a whole bunch of other base carbon chains, whether you're looking at butanol, pentanol, or hexanol. Again, the basic idea here is I'm just adding an OH group onto the molecule. These tend to be much better at forming a liquid phase. Remember, methane, ethane, and propane are all gases. Methanol, ethanol, and propanol are all liquids. And again, they also tend to be a little bit more polar in that they mix much better with water than their strictly hydrocarbon derivatives. So there's also a whole bunch of other things you can replace a hydrogen with. Another option is you can make replace a hydrogen with a halogen. So this is anybody in group 7, also known as halides, because remember, we use that "ide" suffix onto a carbon chain. And again, these will have the same prefixes as the same base name as an alkane. The only big difference is we add in an extra prefix. So for example, if I'm going to add in a fluorine atom, we use a fluoro prefix. Chlorine, we use a chloro. Bromine, we use bromo. And iodine, we use iota. And if I've got multiple different groups present, I list them in alphabetical order. So bromo first, then chloro, then fluoro, then iota. So let's go ahead and see what I'm talking about. So for example, if I have a methane molecule, 1 carbon, and I've replaced 3 of the hydrogens with chlorines, I now have 3 chlorines, so trichloromethane. Again, suffix stays the same. I only add this additional prefix. You may know trichloromethane better by its common name of chloroform. Also, you can add in some fluoros to make difluoroethane, two chlorines, two fluorines. This has the more common name of freon. So one of the dangerous parts about making use of these halogens is it turns out that biological systems are really bad at breaking down molecules that contain a lot of halogens, which is one of the reasons why they were used to be so common, because you didn't have to worry about these degrading with time, as well as they're really good at absorbing heat. And also one of the reasons why you'll find a lot of halogens present in drug molecules, because when you have a drug molecule, you don't want your body to immediately break it apart. You want it to sit in your system and do whatever it's supposed to do. So one of the ways you can do that is adding on a bunch of halogens. Unfortunately, this has a lot of problems for the environment because they don't break down well. And when they do, they often have really weird reaction pathways. And a great example is freon, which would sit in the atmosphere until it has a chance to react with ozone. And this is one of the major reasons we had a hole in the ozone layer, is because freon would react with ozone. So let's go ahead and talk about some more organic molecules. So another thing I can do is I can add in a nitrogen atom. So anytime I have essentially a nitrogen atom in a organic molecule, we tend to call these amines. So amines can be attached to any number of carbon atoms, 1, 2, or 3, rarely 4. And when we're naming them, we essentially name them after the longest carbon chain, and then we throw on an amine suffix. So for example, if I have a methyl group attached to an amine, I have methylamine, which is very common in a lot of reaction mechanisms. We can also throw 3 different ethyl groups onto an amine, and we get triethylamine, which has one of my favorite acronyms in organic chemistry of T. Yeah, it's really fun. But it turns out that triethylamine is occasionally used as a solvent and is often used to facilitate a huge number of organic reactions, as it's really good at moving hydrogen atoms from one place to another using this critical nitrogen. And hopefully we'll bring in some examples of the reactivity of methylamine and triethylamine later in the semester. So one of the last groups that I want to talk about is going to be a special kind of alcohol. So it turns out I can place a alcohol next to a carbon double bonded to an oxygen. This is also known as a carbonyl group. And what ends up happening is it forms a very weak form of oxyacid, which we talked about earlier. And these are called carboxylic acids. These can be described with the same suffix we found earlier, oic acid. So you're going to find a lot of these present in a whole wide range of chemistry, because most organic molecules that have some sort of acidic behavior tend to have a carboxylic acid present. And you'll probably actually know a fair number of these. One of them has the technical name of methanoic acid. You may know it by its older common name, formic acid. And it turns out the reason it was originally named formic acid is because it comes from a biological genre called formates. You know them as ants. Turns out that this is why ant bites sting, is because it injects formic or methanoic acid into your system, where it does all kinds of ugly little degradations. Another form of organic acid is ethanoic acid, where I now have 2 carbons with a carboxylic acid on the end. This has a common name of acetic acid. But there's a whole wide range of different acids out there: propanoic, butanoic, benzoic, and all of these share this same oxyacid. So it turns out oxyacids don't have to be based on inorganic elements like sulfur or nitrogen. Carbon does just fine as well, but it's all based on this more general organic nomenclature. And these are present all throughout nature. So it's good to kind of know what they are, so later we can talk about their fun reactivity. So next time, we're going to go ahead and finish by finding a good way to kind of assess where the electrons are at in all of these various chemical molecules we've spent this chapter talking about. Until then, take care.